Hi, in this video I want to describe the pi-space theory in terms of how one can represent velocity and also momentum. The well-known way to represent special relativity is to use the Lorentz-Fitzgerald transformation. And in order to understand this lecture, you would you would have to have read the introduction to the PySpace theory document, which is on the PySpaceTheory.com website at the time of this recording. You can also search for it if you can't find it there. Um, so the idea is that according to the theory, um, you have pi shells which represent a moving object, and they get smaller as a result of velocity. And also there's the question of how do you model not just velocity but momentum. So in the diagram I show here, there's a yellow pi shell, there's a blue one, there's a red one, and then there's one which combines the two together. Uh, so I'll just go through them one at a time. So the yellow one, it represents the observer, and that is to say the stationary observer. So let's just say it's the person standing on the platform as the train goes by. The blue one represents the velocity, and in the theory of in the physics theory that I've developed, area loss of the observer, relative area loss of the observer in terms of its diameter is velocity. That leaves you with um, uh, a a pi shell with a remaining size, and this is the moving object. And in the world that we live in, typically the amount of movement that we do causes such a small amount of of area change that the red pi shell and the yellow pi shell typically are the same. I'll show examples of that in a minute. And then the other example would be how does a moving pi shell encode the kind of the momentum vector? So the idea is pretty simple. You take the observer pi shell, you subtract the area, you're left with a pi shell of this size. This is the Lorentz-Fitzgerald transformation visually represented. And then momentum is basically the original observer pi shell uh, minus the blue area, which is the momentum part, which is mass times velocity, and this is the actual particle itself. So this is the particle, and this area here is the wave part of um, the object in question. This goes to the Louis de Broglie concept. This is a way of visualizing it in pi space. So I'll just go over it again. The observer is the yellow, is the area loss due to movement. And the remaining pi shell. The yellow one is the relative observer. The blue one is the relative velocity, which is the area loss. The red one is the size of the moving particle after the area loss, which is this one. And then the momentum pi shell is the particle in red with area loss, containing momentum waves in blue, moving in the direction to the right. So the idea is that it's moving this way because this is the largest place where the momentum waves are. And this is how, according to this theory, this is the Newtonian analog of the first law, where an object will continue to move in a particular direction um, if it isn't subject to an external force. So this, you can imagine that this is sort of like some object in space that just keeps going this way, and it knows how to do that because of this momentum shell here. Now, let's do some simple examples. I talk about the different velocities here. So in this page that I have, which is called the pi at the time of writing, it's called the pi shell drawings. It may change later, but for the moment, that's what it's called. It uses HTML5. It's a HTML5 browser, so it just uses the canvas object to draw some circles, and there's a little bit of math involved. I won't need to go into that in too much detail. Suffice to say that this uh, this entry point here uses the Lorentz Fitzgerald transformation, and PySpace is a version of it using cosine, cos arc sine, um, and so on. You need to read the introduction to the PySpace theory and the formulas. I'm not really going to go into that in detail here. I'm just trying to describe how to visualize objects moving in PySpace. So what we have here is 0.5 of the speed of light. So let's take an example where we're going a fraction of, like a very small amount of speed, more kind of analogous to the speed we travel in a car or whatever. It would obviously be much smaller than this, but if I change this, you can see immediately that the diagram changes. This is the observer. The amount of area change due to velocity is a fraction of the size of the observer. So it's this and this form this. So what you have is that the momentum is encoded in here, and it has a very small wavelength, which is represented by the Louis de Broglie, I hope I pronounced that right, wavelength. Now, so in the world that we live in, if we're in a car or we're walking or we see a train go by, the amount of speed, the amount of relative area loss, according to this theory, is so small you don't really see it. In other words, the wave that's associated with this particle is so small you wouldn't see it or feel it. Now let's just say we increase that to be 0.1 of the speed of light. You can see now that the amount of area change here is a little bit larger, which is the velocity, and this that fraction of area loss. Now, a real atom is in the nanometer scale, so it's a fraction of a nanometer scale object. Now, you can use pi shells to represent entire planets. If you read the documentation, you'll know what I'm talking about. But let's just take it that that's 0.1 of the speed of light. Again, these two, the momentum pi shell and the remaining one, they're all very similar in terms of size. There's very little between them, but you'll notice as you get large into like 0.2 of the speed of light, there you see a small amount of here where it's a little bit of a bulge, and then we go to 0.3, and then suddenly the momentum shell starts to form here. So as a fraction of, this is more the wave part of the particle. This is the particle, and this is the wave, and this is the momentum shell, which contains the wave component. And again, we just go back up to say 0.8, which is a better example. And suddenly you see it changing quite dramatically. So this is the observer, this is the actual pi shell that represents the amount of area loss, which is actually greater than the particle. So suddenly you're at 0.8 of the speed of light, and the momentum shell, it's becoming more wave than particle. So that's kind of what that represents. And then we do 0.9, say 0.95, which is close to the speed of light, and suddenly it's mostly wave. Yeah. So you go from a case where it's mostly particle to mostly wave with a particle, which is quite a bit smaller than the observer. And you can just keep doing it until it gets much smaller. So if you're curious about how I've done this, you must read the theory and the formulas. But you can just view you can view the code of the HTML page. It's just using HTML5. All right. So I'll just put it back to say 0.01, and this is more the kind of situation that we're in, that we experience in terms of riding a bike. It's more like 0.0001. So the amount of area change is negligible. So this is why the Newtonian analog works. And then Einstein came in and said we have to fix this, and this is the kind of world that Einstein modeled with Lorentz, and this is how to visualize that world in PySpace. I have a document on the theory which describes momentum, the particle, and the wave. So this is how to visualize this in PySpace, and a little bit of software which isn't that complicated with the formulas can achieve this effect. Alright, so that's how to visualize momentum, special relativity, the Lorentz Fitzgerald situation, and to play around with the input values here. That's it. Thanks.